was working for my 1040 class on Monday, and I thought I recorded the whole thing, and then when I went to play it back, it went like this, zip, and it was done in like less than a second. So we just did a practice run, and it seemed to be recording, so I think we're all set for today's lecture. So if you go to YouTube, you will not see something for class 26. Okay, so if you want to write that down so that you don't write to me and say, where's class 26? And I have to remind you that it didn't get recorded, that would be great. Because you know what, I'll probably forget now. All right, so pull out your lecture notes from Monday, because we had that last page, a couple of things to do, 11 and 12. We want to finish up. And if you look at our schedule, today we're supposed to do polynomial regression, and then Friday, we're supposed to finish up with graphing polynomials, which doesn't make sense because we started 3-2 on Monday. So we're going to finish 3-2 today. So you want to switch classes 27 and 28 on your schedule. In other words, class 27 is the graphs of polynomials. We're finishing this section since we started it Monday. Friday will be polynomial regression. And what that means is your quiz next week is on classes 24, which was quadratic functions, and 25, remember, was a test, so that's not included here. And then section 3-2, which is polynomial and their graphs. So it's Monday's class and today's class. Okay, that will be included with the quadratic functions, which we did last Wednesday before our test. So that will be the quiz next Wednesday. I want to remind everybody that I have 1,000 sign-up times on my door for the next 2 weeks because it's advising weeks. And so I put up tons of open time slots that I'm pretty much available like almost all day, every day. So please feel free to come put your name there for half an hour or an hour. You can put it several times if you want. To get any help you want, or if you have any questions about advising, I'll be glad to help you. I've been here a really long time, 32 years, so I know a lot about transfer and the school and courses and our programs. I used to be the academic dean, so I know a lot about the academic policy. So if there's any questions that you want to ask or whatever, just put your name in one of those time slots, okay? So let's start with number 11, because we had finished off with 10. So if you look at this polynomial function there, you would say, oh my goodness, that looks really scary. And you probably would think that prior to Monday, you wouldn't even have a shot at even being able to visualize the graph. Well, let's see if based on what we did Monday, we can figure out some things about this particular polynomial function. Okay, so the first thing we want to do is we want to find the zeros of this function. Remember, the zeros are equivalent to the x-intercepts on the graph. So that's where your y value, or f of x, equals 0. So to do that, especially when it's in this beautiful form here, which is all factored, we can just look at each factor and say what value of x makes this whole function equal to 0. So if we set each of these factors equal to 0, we've got 4 different factors there. We have an x plus 3, we have an x plus 1, we have an x minus 1, and we have an x minus 3. So if we set all of these factors equal to 0, you can imagine just dropping those parentheses and solving for x. What will be the values we get for our zeros? What will be the 4 different values? Yep, Julia? Yep. -3, -1, 1, and 3. Okay? And then we talked about on our graph, so let's go down here on our little graph. Do you have one of these on your sheet? Okay, just do like a grid. Just do a, y-axis and x-axis and just fill it in. All right, so, or you could just watch. It's okay. When I first did this, I wasn't expecting you to really be thinking too much about graphing it, but I thought it might be a nice little thing. So we got a 0 at -3. So you'd put a little dot at -3. What were the other ones again? So I don't have to keep scrolling up and down. -1, 1, and 3. Okay. So we know something about our graph at these 4 points. Our graph is either going to cross through those points, either from above the x-axis to the below or vice versa, or we're just going to touch it and continue on our way. We don't know yet until we look at the multiplicities. Okay, so let's look at the multiplicities, and remember that's the exponent on every factor. So when it's a 1, you don't see it, so I'm just going to throw it in right there. So the factor x plus 3, if you wrote this out the long way, would be x plus 3 times, x plus 3 times x plus 3. It appears twice, right? 2 factors, that's what the exponent tells you. So the multiplicity is 2. What about x plus 1? How many times do you see that factor in your function? Just once, so it has multiplicity 1. And the factor x minus 1, whose 0 is 1, has a multiplicity of 2. There it is right there. And then finally, x minus 3 also has a multiplicity of 1. So can you begin to visualize this graph? Well, remember, when you have an even multiplicity, you should think of what parent function that has a square. What parent function should you think about? Parabola. So when you have an even multiplicity of 2, you could look like this at a 0, because notice with your parent function, your 0 is right at the origin. Or you could be going downward. We don't know yet. So at -3 and at +1, our function's just going to touch. It's not going to go through the axis. And when you have a multiplicity of 1, what function should you think about that has a degree of 1? A linear function, a straight line, right? So we're either going to go straight through the axis in the positive direction or straight through the axis in a negative direction. But the point is we actually cross the x-axis when we have an odd multiplicity. So odd, we cross the x-axis. Even, we just touch it. Okay? So if we go down and we start to think about the graph, don't forget, one of the key ideas about sketching these graphs is trying to find out the degree of your polynomial. Now, when your polynomial is written out in its regular form with adding and subtracting, you just look for the highest exponent. But this polynomial is in factored form. So in order to figure out its degree, we have to add all the exponents that appear above each factor. So I'm going to put in my 1s just so I don't willy-nilly just forget them. Okay, so to figure out the degree of this polynomial, I just add up 2 plus 1 plus 2 plus 1, and that gives me 6. Okay, so that tells me something. If I have a degree of 6, what do I know about my end behavior? What do I know about my arms? They're the same. My arms are either both up as I head towards positive and negative infinity, or they're both down. So I know my end behavior is going to be the same. And what else do I now need to determine? I need to determine, are my arms up or are they down? Do they go up like a happy parabola or do they go down? And how do we figure that out? Do you remember? The leading coefficient, right, which is right here. It's 1/9. That's our leading coefficient. So our leading coefficient is 1/9, and it's positive. 1/9 is positive. It's bigger than 0. So we know that this graph, however far out on the, however far we go in the left-hand direction on our x-axis or in the right-hand direction, we're going to be rising towards positive infinity. That, another way of saying that is this function, the values of this function are increasing without bound. They get bigger and bigger and bigger. Okay? So what do I do now? Well, we don't know a lot, except we know something about each of these multiplicities. At -3, we know we're going to look like a little baby parabola heading down there. So I'm just going to start up here, and I'm going to come down, and I know I don't cross it, I'm going to turn around. So here I start to turn around. Now, I don't know how far up I might go before I start heading back down towards this 0, and that's not important right now. We're just trying to get a quick sketch, all right? But I do know at -1, I'm going to cross through my x-axis because my multiplicity is 1. I'm going to act just like a line. So for now, I'm just going to scoot up here and come straight down here, all right? Now, you could find where it crosses the y-axis by putting a 0 in here, but that's today's work, so I'm not really going to be too concerned about that. We're just going to do a quick sketch. So now you've crossed down through, you know you got to head back up towards 1, because that's another 0. And what happens at 1? You're not going to cross the x-axis, you're just going to touch it and come back down. So even though I could find the y-intercept, I don't really care about it right now. I just know I'm going to cross here and head back up here, but I'm going to turn around again, and I don't know if I come way down here and then come back up, or I take a really quick turn. I don't know. But that's a quick sketch of what that graph might look like. Just by knowing where you cross, what your multiplicities are, and your end behavior. Now, when you take calculus, you're going to be able to find the exact spot where you have all of your relative maximums and minimums right here. You'll be able to find where these points are, okay? Because calculus will do it like that for you. It's just something called the derivative, which you don't know yet, and you're finding when that derivative is 0, because if you think about a line touching that point right there, it'd be horizontal, and the slope of that line is 0. So anyway, I better not talk too much about calculus. So anyway, so you come down, you go straight through. In fact, this is a little off here in my drawing because this looks like I'm turning there, but I'm really not. I'm coming straight down, I'm crossing, and then I'm coming up like that. Okay, so that would be what we could do based on Monday's lecture, okay? We're going to be able to really hone this in today and do a little better job than this. Any questions on finding zeros and multiplicities, which was part of Monday's lecture? Any questions before we move on? All right, let's take a look at the final thing. We've reached a turning point, no pun intended. Absolutely, the pun was intended. All right, so turning points here are at -1, 6, and at, I can't see this whole thing, but if I look at someone's notes here, what does it say? 1.5 and -0.875. Okay, so let me write that in. So we have 2 turning points here, 1.5 and -0.875. Okay. So if I asked you what the degree was of this function from looking at the arm behavior, what type of number is it, odd or even? Odd, because your arms, right, are going in opposite directions. I know I'm missing part of it. Yeah, remember I told you my graphs haven't been coming out. So what's the last part I need, Julia? Julia? Minus 4x plus 4. Thank you. So the degree of this function is a 3 because you have your function right there. But you probably would have known it was odd because you do know it's odd because of its end behavior. You know it's definitely not 1, right? Because it's not a straight line. So you know the minimum degree, minimum it could be, is 3. Can't be 2 because it doesn't have its arms going in the same direction. So the smallest degree it could possibly be is a 3. It might be 5, I don't know, but it could be a 3. You definitely know because the function's given to you, okay? But if you didn't, you could guess that its minimum degree would be a 3. How many zeros, real zeros, does F have by looking at the picture? How many real zeros? 3, right? It crosses the x-axis in 3 places. There you go. So it has 3 real zeros. Okay. And how many turning points does it have? That's what we've been calling relative maximums and relative minimums. But how many turning points does it have, Orlando? 2. Okay, so how are we defining a turning point here? A turning point, well, let's see what happens at the turning point. Here's our first turning point. What can you tell me about the behavior of the function? Just as I'm moving towards that turning point, and then after I move to the right of that turning point. What's happening to the function? Why is it being called a turning point? Anybody? Yeah, Brendan? It changes from a positive slope to a negative slope. Okay. Right. All right. So what's happening that's positive here? How do we define functions on the interval from -2 to -1? What do we say this function is doing? It's increasing, right? So at the first turning point, and that's why we call it a turning point, our function changes from increasing to a decreasing function, right? So it's increasing on what interval? Remember, this is always over your x values. So it's increasing from -infinity to -1. That function is increasing from way down here, down, all the way up to -1. That function's increasing over that interval. So this is the interval. So those of you who didn't remember what that meant on the test, you always talk about increasing and decreasing over an interval. Your book makes it an open interval, parentheses. Okay. Excuse me? Yeah. So it changes at -1 and then it becomes decreasing. So what's the interval this function is decreasing on? -1 to where? 1.5, right? Right to that other little point, our other little turning point. So from -1 to 1.5, we're decreasing. And then what happens after 1.5, -0.875? What happens to the function then? It starts to increase, right? So it starts to increase again at the next turning point, which is what? 1.5 to positive infinity. So at each turning point, your function changes its mind. Okay, it's fickle. Okay? It's like, you probably know some fickle people in your life. 1 minute they're saying one thing and next minute they're saying another. Well, the same is true with polynomial functions. At the turning point, just prior to that point, you were feeling one way, really positive, increasing, and then afterwards you start your decline, you're decreasing, and then you start increasing again. Probably like mood swings, right? We all have these every day. So that's what happens with polynomials. They're very moody functions. Okay. So in general, if f is a polynomial function of degree n, this is like a little, really important fact here, so you might want to put little stars around it. If you know your polynomial has degree n, you know something about it right away. The graph of f has at most n-1 turning points. Notice, this was a degree 3. We had n-1. N was 3. Take away 1. At most, we have 2 turning points. At most. That means the maximum number. You'd never see a degree 3 with 3 turning points in it. That would have to be a degree 4 or higher. And it has at most n real zeros. So this function has at most 3 real zeros and at most 2 turning points. But not all cubics have at most. For example, think of your parent function, x cubed. Think about x cubed. How many zeros does x cubed have? Just 1. See, so it doesn't mean it's always going to have 3. It's at most 3. So this has 1 real zero. How many turning points? None. This function is increasing always over the whole x-axis from -infinity to positive infinity. It's increasing. It gets real flat in here, but it's never a horizontal line. It just gets closer and closer and closer, and then it comes out like that. Rando? Who's Todd? Yeah, that's calculus. He's talking to you about the derivative. That's what I was sort of referring to earlier, but I didn't want to get too technical with the calculus. And on a curve, what the derivative does is it gives you the slope of the line tangent to a point. So if you come to this point and you take the line tangent to that point, it will always be horizontal. So at your relative maximums and minimums, your slope's always going to be 0. So your derivative is always 0. So that's what he was referring to. Okay. Any question on turning points? Now remember, this information here at most is very important. Doesn't mean it will always have 2 turning points and 3 zeros. It just means that's the maximum number if you have degree 3. Okay, so let's start today's material, which we've already done a little teeny bit of with number 11. So now that we know what end behavior is, zeros, multiplicities, and turning points, we're actually going to be able to get some real quick sketches of polynomial functions. So let's take a look. Your book lays out 5 steps for you, which is really nice. It tells you how you start to approach graphing these functions. So here's a polynomial, x to the 4th minus 6x cubed plus 9x squared. Again, it's kind of a powerful feeling, like, because before this time, all you knew how to really do was maybe sketch the graph of straight lines and parabolas. Now you can look at something like that and you're going to be able to get a pretty quick and accurate sketch of it by just going through these couple of steps. Okay, so first of all, you look at that. Now when I start, the first thing I think of is what degree do I have? Is it odd or even? And that's the very first step, because that's what the end behavior is going to help you with, is how does this function act as x goes towards positive and negative infinity? Does it rise? Does it fall? Where does it rise and fall? So the first thing we have to do is to determine the end behavior. The leading term, know that language, leading term is x to the 4th. That's right here. That's your leading term. If you wrote it out exactly how it's intended, you put the 1 in front of it, even though we don't see the 1, is x to the 4th. The leading coefficient is 1. That, remember, that's what we've been calling a sub 4, because our degree is 4, so our leading coefficient would have the name a sub 4 is 1, and it is positive. So right away, I know that both of my arms will be going in the same direction. And what direction will they be going, since 1 is positive? Up. All right, so before I even sketch this graph, I know something about how it's going to behave as x moves out towards positive and negative infinity. So down here on my graph, I can just do this kind of thing. I'm just going to put my arms going up like that. Just real quick, I'll kind of go in and adjust it in a minute, but that's what I can get just from looking at the leading term. I get that information. Okay, now I know the next thing that's really important is to find where does the graph of this function cross my x-axis. That's called the zeros of the function. It also appears as x-intercepts. And I know I can find those by setting my whole function, the y value of my function, equal to 0. F of x is 0. So I just set my function equal to 0, and I solve this equation. That's why the whole beginning part of the class, we had to learn how to solve equations like this so we could then apply them for graphs later on. So the only way I can possibly solve that equation is to remember my greatest common friend is x squared in this case. My greatest common factor is x squared. So I factor out x squared. So I automatically know right away x squared equals 0 only when x is 0. I already know one of my zeros is going to be x equals 0. But when I look at that factorization, I have to determine, is it completely factored? Is it factored into all of its primes? Well, I can't do anything with x squared. I could call it x times x, but that's not going to get me anywhere. So now I got to look at this. This is what you've been calling all along second degree trinomial. And so you say, what are the factors of 9 that add up to 6? The factors of 9 that add up to 6 are 3 and 3. So you factor that one more time. X minus 3 times x minus 3. And now you can express that factorization using an exponent. And the exponents are important because it helps us with our multiplicity. So you make it more compact by using your exponents. So I've now factored that completely, and I can look at each factor, set it equal to 0, and solve for x. So x squared equals 0 when x is 0, and x minus 3 is equal to 0 when x is equal to 3. So I've got 0 and I've got 3. That's the two places that this graph is going to have zeros. So 0 and 3. All right. Now, what am I doing at 0 and 3? Well, we'll get there in a minute. Okay. You're touching, right, because the multiplicities of each of these zeros is 2. So at the 0, x equals 0. So at that 0, I'm touching. I don't know if I'm touching it this way or if I'm touching it that way. I haven't figured that out yet. I know I'm not crossing at that point. I'm just touching. And at the 0, let me just get that little blurby out of there. There we go. And at the 0, x equals 3, I'm also touching. And I'm either touching above the x-axis or touching below the x-axis. I don't know yet, but I know something about my behavior at those zeros. All right, well, let's find the y-intercept because that's going to help us. We'll know where we're crossing the y-axis. The y-intercept is always computed by throwing 0 in for x and seeing what's hanging out in the end, what the constant is. Do we have a constant here? Constant term? No, so it's going to be 0, but let's go ahead and do it. 0 to the 4th minus 6 times 0 cubed plus 9 times 0 squared. That's all 0. So 0, 0 is acting as both the x-intercept and the y-intercept. The origin often plays that role. Just think about your baby parabola x squared. That's the vertex, it's the x-intercepted, it's the y-intercept, it's all those things. So we're also going to have a y-intercept at 0, 0. So the last idea, and this is going back a few weeks, is the idea of, does this graph have symmetry? Because if it has symmetry, then once you draw one side of it, you can think about just flipping it over and drawing the mirror image, either over your y-axis or over your origin. Even symmetry is like what we think about with our parabola. So if you put in opposite values for x, you come out to the same y value. Odd symmetry, remembers, like our cubic function. If you put in opposite values, you come down, your f of x values are also opposite. So in other words, just think real quick of 1, 1, and 1, negative 1, negative 1 on your cubic. Okay? So here we have 1, 1, and here we have negative 1, negative 1. So when you put in opposite values, here are opposite values of x, 1 and negative 1, the y values are opposite. So that's why they say the value of the function at the opposite x value is the opposite of your original value, f of x. Right? So this is even and odd, but sometimes a graph doesn't have any symmetry, so it's neither. So let's look at this graph and figure out what kind of symmetry it may or may not have. I don't know. I haven't even done this problem. This will be my first time. So let's think about it. Does f of x equal f of the opposite of x? In other words, if I throw in 1 into here, let's just play with the number first, and then we'll do it generally. If I put in f of 1, is the y value for f of 1 the same as it is when I throw in its opposite? Let's see. 1 to the 4th minus 6 times 1 cubed plus 9 times 1 squared. What do I get when I put that in? I get 1 minus 6 plus 9. 1 minus 6 is negative 5, plus 9 is 4. So I would be at the point 1, 4. Now, if this has even symmetry, when I throw in negative 1, what's my y value going to be? 4. It's going to be the same, just like my parabola. So let's see what happens when I throw in negative 1. I get negative 1 to the 4th minus 6 times negative 1 cubed plus 9 times negative 1. Let's see what that is. Negative number raised to an even exponent is 1. Negative 1 cubed is negative 1. Oops, that's going to change the sign, right? It's going to change the sign. And bless you. And then we get negative 9. So there's no way this is going to end up being a 4. So this doesn't fold over the y-axis. Okay. Now, I haven't proved that. I've only shown it for one value. So if you want to show it for all values, you have to say, here's f of x. F of x is this function. Then you have to show what f of negative x is. And so you just replace x with its opposite. And you can automatically see, I hope. Oh, this is supposed to be squared, right? So that's plus 9. You can automatically see the minute you do that, look, these two are going to line up and be the same because it's an even power. So a positive number raised to the 4th power and then its opposite is going to give you the same value. 2 to the 4th and negative 2 to the 4th is the same. Same thing out here with your 9x squared. If you throw in opposite values and you square them, you're kosher. But look at that middle term. When you cube x and then you cube its opposite, the signs are going to change here. So f of negative x is going to equal x to the 4th. And you say, whippy, yes, maybe it's really happening. But the minute you get x, negative 6 times negative x to the 3rd, that becomes plus 6x cubed. And that's where you run into trouble. There's no even symmetry here. Yeah, Orlando?
We generally say that if there's entire equations to an odd degree,
if the entire equation is to, you mean every term's odd? It's,
no, if you add up the,
oh, if you add these up and you get an odd,
yeah,
it won't have even symmetry? Yes, I think that's right.
Even.
Right, so it doesn't have even, but does it have odd symmetry? So that's the next thing we have to figure out. So with odd symmetry, when we throw in opposite x values, the y values are opposite. So let's see, we're trying to figure out if f of negative x is the opposite of f of x. Well, what's f of x? Here it is. Here's the function right here. X to the 4th, blah, blah, blah. So let's see. Let's put that in. X to the 4th minus 6x cubed plus 9x squared. That's f of x. I'm going to take the opposite of all that. So let's see. Negative x to the 4th plus 6x cubed minus 9x squared. So I've taken care of this part of my equation. I've just taken the opposite of my polynomial. Now I have to evaluate my function when x is negative. So when where I see x, I'm going to put in negative x. So let's do that. Negative x, negative x, negative x. So what does this give me? X to the 4th. Do I have to go any further? Because look, already they're not equal. So the moral of the story is this graph's not going to have even symmetry or odd symmetry. Okay, it's not going to have any kind of symmetry. All right, that's fine. So let's use the fact that the maximum number of turning points, what's the maximum number of turning points for this? 3, it has degree 3. So the maximum number of turning points will be, excuse me, does it have degree 3 or 4? Degree 4, I already did the subtraction of 1. The maximum number of turning points is 4 minus 1, which is 3. So I can have 3 turning points. And what's the maximum number of zeros I can have? Real zeros. I can have 4 real zeros. But how many do I have from looking at my graph right now? 2. I just got 2 little dots along the x-axis. So I can have a maximum number of 4 real zeros. I only have 2 in this case. And I know I'm touching. So what do I know? Well, I know my arm's probably not going to be way out here. I'm just going to start a little closer, like in here. I'm going to come down, and at 0, 0, I'm going to turn around. My mood right now is negative. I'm going to turn around and become positive. Oops, what happened to my other 0? How did that disappear? Didn't I have 2 dots on there a minute ago? I did? Wow, that was pretty neat. What was my other 0? 3? Okay. So I'm way up here. And as I approach my 0, I'm coming down. I'm decreasing on that entire interval. But once I hit 0, I turn myself around. I reach my low here. I turn around, but I know I've got to head back in towards this other 0. I'm going to be negative for a while again. And then, woohoo, I'm positive for the rest of my life. Okay. So there you go. That's a quick sketch. I don't know how high up this thing comes before it turns around. It might actually just go like this. Look, loop, and come back down. I don't know, right? It could do anything. It could go really high up, or it could be really a small hill that Liza would even want to walk up, right, Liza? Yeah. All right. So that's a quick sketch. Okay. Notice this doesn't have symmetry about this axis or about the origin. It would actually have symmetry right in through here if we knew that point. Yeah. Yeah.
If you adjust it, would you say that?
Well, it has symmetry about that. That would be the axis of symmetry for that. Just like with a parabola, it's not always the y-axis your parabola is symmetric about. It's wherever you shift it, right? So it kind of looks like a W, doesn't it? Has 3 turning points. Look, 1, 2, 3. 2 of them are your zeros. Okay, so there's your 3 turning points, your maximum number of points, and your 2 zeros. Okay. Yep, Megan. How I found the turning points. Okay, these are our zeros. Okay, and I know that at that 0, I'm going to look like a baby parabola. Okay, so if I start it all over again, all right, at that 0, right there and right there, I'm going to turn around. Now, how do I turn around? Well, since I know that I'm going to start off above the x-axis and end above the x-axis, I can't be coming from this direction to turn around, you see? So I know I'm coming in. I'm really positive. I'm coming in, and right at that 0, I'm going to look, if you just zoom in right there, you just take a picture of that, right in there, and you blow that up, it looks just like a parabola because it has multiplicity too. Okay? And then I know at this point right here, Megan, I'm also going to look like a baby parabola. Okay? So I got to turn around. I've got to come up and reach a real kind of like hill at some point. And again, I don't know if I just kind of go like that or if I really come way up here like this. I don't really know. And it's not really important. What's important is that you have this W shape. And like I say, you could play around with some what they call test values. You could find some values between 0 and 3, plug them into your function. You could have your calculator do that. Here, let's do it. Plug in some values in your function, in your calculator. So if you wanted to just play around with this, I mean, your graphing calculator will give you the whole thing, but if you just wanted to play around with some values, what is this? X to the 4th minus 6x cubed, right? What was it? Minus plus 9x? 9x squared, is it? All right. All right, so let's say we don't want to graph it yet, but you just want to look at some values between those 2 zeros, Megan. Those zeros are at 0 and 3 because you want to see how far up might this go. So I'm just going to go to my table. I'm going to set my table. I'm going to start at 0, and I know my answer will be 0 when I put 0 in. And I want to go to 3. And let's take, whoops, we want to increment by, let's say we want to increment every half, just to see how high up we go. Then I go second table and actually look at the values of my function. So notice at 0 and 3, I'm 0. And what does my function do? At a half, it goes up to 1.5. At 1, it goes up to 4. And where does it appear that the relative maximum might be? Somewhere around 1.5, right? Because that's its highest point. If you want to get in a little bit closer to actually look at it, make your increments smaller in your table. Go down here and go to like 0.1 if you want. The calculator's doing all the work, so let it work. So there you go. Let's see. We start off at 0. We're rising. We're rising. How far do we go? Let's see. We know we're going up to at least 5. Do we go? Oh, 5.06. So at 1.5, it looks like that's its highest peak, right? And it's at 5. It's a relative. It's a relative maximum. Right? So. Yeah. Yes. Yes. Yeah. So it's going to go up a little bit more than 5, right? 1, 2, 3, 4, 5. And it happens about right there. So now we can sort of get a more accurate graph. Okay. Now you could have quickly thrown in the value 1, the value 2, and 1.5, and you would have had a sense that it didn't go way up here to 20 or 30. And it didn't stay way down here, say below 1. But again, that's not what we're shooting for. We're just trying to get a fairly quick sketch. So I want you to try the next one at your seats. Here it is. Follow those steps. I made it look very similar to the one we did. So you got to use your greatest common friend to find your zeros and work away at it. Use your little flags if you need help. I'll be glad to come around and help you out. This is kind of fun stuff, isn't it? Exciting. You're all excited. What do we find for the zeros on this first one? Real quick. Okay, sketch 0. What was it? 0, -3 and 2. Is that right? Positive and negative. So we got 0, positive, and -2. We know it's an odd function. So arms are in different orders. And since our leading coefficient is 1, my right arm's up. So my right arm's up, my left arm's down. When I factor this thing, I have x on the outside, x, what is it, minus +2 and x -3, right? So in factored form, all of my zeros have multiplicity 1. I'm going to go straight through. What's my intercept is the same as 0, 0. So I know I'm going to go straight through this one. I'm going to come up, then come down, go straight through that one, and then have to come back up. I don't know how far up I come or how far down I come. But I have 2 turning points because my degree is 3. And I have 3, at most 3 real zeros, and I happen to have 3 real zeros. So again, I don't know, like maybe this turns around like right here, just barely gets above the x-axis. Doesn't matter as long as you have the general shape. Okay, let's talk about the symmetry stuff. I'm going to do a little. We did this a while ago, so it might be a little teeny bit fuzzy. Okay, so just tell me the function again. F of x is what? X cubed minus x squared minus 6. All right. So this is an odd function, right, folks?
Correct.
It's an odd function because its degree is 3. An odd function cannot have symmetry about the y-axis. So you knock that possibility. So the question is, does it have odd symmetry? And to have odd symmetry, it means you have symmetry about the origin. Which means if you evaluate your function at x, and you evaluate your function at the opposite of x, your results are not equal. They're not equal, they're opposite. So let's throw in our function. Let's do the right-hand side first. We bring this negative sign down, and let's put in my function f of x. So what's my function f of x? It's x cubed minus x squared minus 6x. Now I'm going to take the opposite of every single thing. Minus x cubed plus x squared plus 6x. So that's the opposite of my y value. All of them. All of them. Now my goal is to put negative x in where I see x and do everything my function says. And if the left side equals the right side, I have
symmetry about the origin. If they don't, I don't have any kind of symmetry. So now I go back to my function. Everywhere I see an x, back here in my function, let's highlight everywhere I see an x. Highlight it out. Everywhere I see an x, I'm going to put parentheses on it. I'm replacing it with its opposite. Negative. So it's going to look like this. Negative x cubed, take away negative x squared, take away 6 times x. And now I simplify that. And if once I'm done, it looks just like this. Great. And if not, no symmetry. So what does negative 1x cubed? Now you've got to use your exponent. Negative 1 gets cubed, which is negative 1. X gets cubed. So that looks like that. So far you're like, those two are the same. Then you come in here. Negative 1x squared, this negative 1 gets squared, and the x gets squared. That gives me 1x squared. Cool. Right. So it doesn't have any symmetry. All right. Let's take a quick look at the next one together. Yes?
You also tell it zeros are 2 plus 0.
Don't have even symmetry, right? I mean, if you have zeros that are equidistant from one of the other zeros,
Well, wouldn't it,
what do you say? I would. Oh, you have a negative
whether,
two.
whether it has even symmetry or
Odd
odd
symmetry.
symmetry, then you have to go zero.
You would have to go to the symmetry. Okay, so that's another way to tell. I wanted you to have the mathematical way so you can tell all. That's another way. You had negative 2 and positive 2, okay, chances are you have odd symmetry. Now, let's just do the next one, and then I want you to be able to play around with those matching polynomials. Yeah, look, this is already factored out for you, right? So you don't have to do any factorization. Thank you, thank you. Okay, but now you can't just look for your highest degree to find out your degree because it's not an addition subtraction, it's not an polynomial. So now, how do you figure out what the degree of this polynomial is? How do you figure out what highest degree is? You add them all up. So the degree here is 2 plus 1. So it's even. And the leading coefficient would be negative 1. A sub 4 would be negative 1. So that means I'm going to do a droopy. I'm going to have both my arms down. That's always. My x-intercepts I can find real quick by looking at each factor. X squared is going to be 0 and x is 0. X plus 2 is going to be 0 and x equals negative 2. And x minus 2 is 0 and x is positive 2. So we know we're even here. So you think we have even symmetry here? Yeah. If you go ahead and check out f of negative x and f of x, you get exactly the same function. So they all have multiplicity of 1 except for at the origin. So you're going to start negative, you're going to come through negative 2, you're going to come through it, you're going to come down. 0 is multiplicity of 2, so you're going to turn around. Now you turn. But again, I don't know how high up, but the axis I go. That's good sketch. Okay, so I want you to skip 5. It's just redoing the same thing. What I'd like you to do first is your matching of polynomials. You go back to the matching of polynomials, which looks like this. You match up the polynomial with the function that's there. And then go back and try doing some of the give examples of. Do not use your calculator because you can figure out which graph goes with which without. No calculators. And I'll probably do something like this on a test.